Where previously we used rectangles because of the ease with which we can add up those areas, just it's such a simple area formula. And we had the advantage before that all the functions we dealt with allowed us to take limits as n goes to infinity. And that allowed us to get exact answers, and that's what led to our trick, the first fundamental theorem of calculus, which led us to the definite integral process, the great trick. But as you might expect, the very same functions that we can't take integrals of are functions that we also couldn't take infinite limits of. And so we can't really even use the old tried and true rectangle approach that we used before. And so we had to do something different. We got to pick maybe a slightly better shape now, because the rectangles, we can't take infinite limit, we can't add up infinitely many of those guys and get an exact area. The rectangles don't actually match the area under the curve very well, because they've got squared off tops, and we instead opt for a trapezoid. Trapezoid fits the function pretty well, and I think we drew a little picture just to kind of demonstrate this. If we have some function and we want to add up the area under this curve from A up to B, and I'm just going to break this thing up into a series of vertical cuts. I'm going to slice this thing into pieces like we did in the past. Something like that, right? Then the rectangles don't fit super well, right? But if I turn those into trapezoids, all of a sudden they do fit pretty well. Right? I mean, that's not bad. That's not bad. And if we get a large enough number of those so that the intervals get smaller and smaller, the fit even gets better. And we actually, we looked at a couple examples where we added up an area using this trapezoidal rule. But things everybody's not familiar with that. Let's do that again real quick before we go any further. So, who can remember? See if you can do this without looking at. Just see if you can. If you can't, that's fine. But just try. Does anybody remember what is our trapezoidal rule formula? The area under a curve by the trapezoidal rule approximation was what? And keeping in mind that a lot of the stuff is the same as before. The interval is going from A to B, and we've got n total trapezoids. B minus A, B minus A over 2n, good, times, okay, f of A plus f of B plus 2 times what we call the interior sum, right? Sum of okay, good. F of x sub I, but let's go ahead and just write that in. That's always just going to be A plus I delta x, right? Just like it was before. Okay. F of A plus I delta x as I goes from 1 to n minus 1. Okay. And that's our trapezoidal rule approximation, right? That's the one. So we can close this thing up now. Right, we're going to take this, we've got this constant multiplier that we've pulled out in front of the whole thing. We've got the function evaluated at the left endpoint, left edge of the interval, plus the function evaluated at the right edge of the interval, plus 2 times the function evaluated for every step in between, right? This is really, if I is 1, that's just x sub 1, x sub 2, x sub 3, and so on, up to x sub n minus 1. Keeping in mind that really A is just x sub 0, and B is where we end up after the last step. Taking our nth step That's where we end up. So all this stuff is the same as before. We calculate delta x the same as before, right? Delta x is just b minus a over n, right? Okay, and so all we got to do now is just evaluate that. So I think, did we do a trig? We did a trig one last time. Yeah. Let's do a non-trig one. Let's just try. Let's use this to estimate. Thank you. So what if we wanted to estimate the trap for n equals, I don't know, 21. Let's estimate the area under the curve f of x equals square root of x plus 1 from, how about from 0 to 5? It's arbitrary. Okay, using the trapezoidal. Okay, so what are we going to get here? Okay. Okay, so over 42. Okay, there's our multiplier. F of, okay, at where though? 0. Okay, so we're going to evaluate this function at 0. If I put 0 in for x, I just get 1 plus f of, okay, square root of 6. Okay. Plus 2 times the sum of, okay. Okay, so now we've got the function evaluated at, everyone see if you can figure this out. What's going to go in there? What's going to go in there? If it's f of a plus I delta x, what is that? Maybe let's figure out what that expression looks like. 0 plus I times 5 minus 0 over n, but what's n? 21. Is this all making sense? Yeah. 5i over 21. So it's just 5i over 21, isn't it? A plus I delta x, 0 plus I times 5 over 21 is just 5i over 21. So I'm evaluating the function at 5i over 21, so what's that mean I'm going to do? It's going to look kind of awkward, but isn't that what just goes in there? Right? F of x is the square root of x plus 1. F of junk is the square root of junk plus 1. Right? Does that make sense? So all that stuff is going into there. Let's just write what that. Whoops. Let's just write what that is. Square root of 5i over 21 plus 1 as I goes from 1 to 20. Good. Okay. And this is a numerical method, as we talked about earlier, right? Meaning this is one, and this is a huge part of math. Numerical methods are there to use the power of just raw calculation to try to make an approximation of an answer. So this is definitely something we're going to do with a graphing calculator. So then, how would we enter this into the graphing calculator? Let me pull up a calculator. You guys tell me what this is going to look like. Okay. What do? Okay. 5 divided by 42 times. Open up a set of brackets because we have to have that. That's times a whole bunch of stuff, right? Times 1 plus square root of 6. Good. Plus. Now, how do we do this? So now we got to add this sum. 2 times. And then remember, how do we get to sigma?
Math 0.
Yeah, I need math down to option 0. And I got to scoot over. And look what that gives us. It gives us that sigma notation, which is really slick. So then if we go back over, fill in this particulars, we'll just call this x, how about? Call our index variable, instead of an I, we've got an x right there, so we'll just call it x. X goes from 1 to 20 of the sum of that, right? So the square root of 5x divided by 21 plus 1. And if you want to, you could even use that fancy fraction template in there to make it look really cool. But, you know, that's probably good enough. Now, what's the last thing I'm forgetting? You got to close on the right. Good. So if I go clear over to the right, I've got a set of enclosed parentheses around the sigma, but I also have to include this other bracket that's enclosing everything, you know, all this stuff that's being multiplied by the 5/42, right? Can't forget that. So one more bracket, and then if I hit go, it's going to think for a second. It's going to tell me that's the answer. Right? So that is the trapezoidal rule approximation of the area under the curve. Let's just see how good it is, just to, you know, kind of for curiosity's sake. How would I find this actual answer? I'm trying to find the area under this curve from 0 to 5 using the calculator's improved ability to do a numerical approximation. I could just graph the function, yeah, right? We've gone through that, right? Everybody's seen that, I think. We could graph the function and then do, well, let's just do it. So we could graph square root of x plus 1 and make the window go, I don't know, 1 to 6 or something. We'll just go zoom 0, zoom fit. Let the window scale itself up. I'm going to make y min go down to -1. So there's our function. And then all we have to do is second calculate. And which one is it? Not surprisingly, if you want to add an area under the curve,
7.
number 7. It just wants a lower limit, 0, upper limit, oops, what did I do? Lower
It's
limit.
not in your window.
Oh, it's not in my window? Oh, you're right. There we go. Okay. So second, 7, lower limit 0, upper limit 5, and we were close. 9.1312923. 12 something, yeah. And then the other way to do this, yeah, good. The other way we can do without having to do this graphically is if we just go math and then go down to number 9, where it gives us the definite integral template. So I can just go 0 to 5 of square root x plus 1 dx. looks like a normal definite integral. Now we can compare them on the same screen. So we can see that we're close, but, you know, I don't know, is that good or bad? Depends on who you're asking or what the situation is, I guess, right? Okay, but what did we say the weakness was of that? That's pretty cool. Formula works, and it's actually pretty easy to use, but what's the weakness?
You never know how many trapezoids to use.
How you gonna know? How you gonna know how many trapezoids to use? I just pulled that out of the air. 20, 21 trapezoids just sounded good to me at the time. But how do I know if that's enough, right? So there has to be some way for us to define what's the minimum number that we need to get a certain accuracy. And there is, and that's the topic of today. That's the last thing we got to do on this section. So if we just backtrack for just a second, here is the formula, the error formula for the trapezoidal rule. Okay, this is, let me just kind of talk you through this. It looks kind of weird, but it's not that big a deal. So what this says is that for our error to be less than or equal to some minimum threshold, this is the formula that we use. B minus A cubed over 12n squared. That looks familiar, right? But this part's a little strange, this part right here. What this is saying is the maximum value of the second derivative of the function over our interval from A to B. Okay? And that's a little bit strange. Now, all you really have to do, though, because what we're trying to do is come up with the minimum number of trapezoids that we need to do the job, to get the accuracy that we need. So think about this like an engineer. If we were going to err on the side of how many trapezoids we were going to use, would we rather have more than we need or less than we need? More, sure, right? If you have a few too many trapezoids, all that means is that you're going to get an answer that's even closer, right? And so this isn't telling us that this is the exact number, it's just telling us that this is going to give us the minimum number that guarantees that we're going to meet whatever tolerance we define. Okay? Now, how are you going to get this part right here? Well, this is a little bit, I mean, maybe even with a graphing calculator. We just want to know if I find out what the second derivative function is, all I have to do is find its maximum using any means at my disposal. I'm already using a graphing calculator to do the trapezoidal rule. So, I mean, I think that's fair game, to graph the second derivative and just look for its maximum graphically from A to B. And whatever that value is, that's what goes here. It's just a number, okay? So let's do a problem like this then. So let's say we'll use that formula. And let's say this is the kind of thing you're going to get for this. Well, let's pick one out of the book. Okay, how about we'll do two things with this. Let's do one where we just say we want to let's use the trapezoidal rule to estimate the area under x cubed from 0 to 2 with n equals 15. Okay, let's just first of all use the error formula to see what is the maximum error that we're going to get with n equals 15. Okay, how much error can we expect at worst, right? So our formula then, E is less than or equal to, remember what it was? Good, B minus A cubed, good, over 12n squared times that weird thing of the absolute value of the second derivative, right? Okay, so to do this, now what is f of x for us? X cubed, right? That's the function that we're looking for an area under, right? So there's f of x. So we got to calculate a second derivative. what's the first derivative? Second derivative, 6x. Okay, so now we want the maximum value of the second derivative from 0 to 2. Okay, so this is just a line, isn't it? Right? We know what this looks like. It's a line with a slope of, with a y-intercept of 0, right? So if I were to graph this guy, it's just doing, it's going through the origin and it's just going up like that, right? So there's 0, there's 2, and so the maximum value, wouldn't you agree, is pretty clearly going to be at 2. Does that make sense? Okay, so this part right here, the maximum of the absolute value of the second derivative just equals the absolute value of f double prime of 2. So what's that going to be for a number? Say it again? 12, yeah. So that's 12. So 12 is the number that goes into this part right there.
How do you know it's 2?
Because we're going from A to B. Okay? Does that make sense to everybody?
What if the bottom wasn't there?
If the bottom wasn't 0, then we have to be a little more careful. If the bottom had been like -3, then we would have had to have drawn this line back a little further. And actually, in that case, the answer would have been, the absolute value of the function would have been bigger at -3 than at 2, wouldn't it? Because at -3, we would have gotten a y value of -18. Absolute value of that's +18, right? Okay? Make sense?
Maybe you just get the bigger number.
And so, yeah, right, so we want the biggest absolute number, positive or negative, on our interval. And on this one, I'm not going to graph this one because it's so easy, it's a line. But we'll look at another one in a second where we'll just use the graph to do this instead. So we got 6 for this, and these numbers are pretty straightforward. N is 15, B is 2, A is 1, or A is 0, sorry. So I can plug those in and get my error pretty easily from this one. Right, so we get our error is going to be less than or equal to 2 minus 0 cubed over 12 times 15 squared times 6. And that's just a number. And that number is what? Let's see. So 8 over 12. It was, oh, is it 12 in there? Oh, sorry, 12. Did I write 6 up there for some reason? Or there? Okay, now one thing we can do, look at this. The 12s, how about that? They just cancel. That's convenient. So I just get 2 cubed is 8 over 15 squared is, what, 225? Yeah. And so that's the maximum error that we're going to get. Our error will be less than or equal to that number if we use the trapezoidal rule and calculate an area with n equals 15. Okay? That make sense? So if we get an answer, and we know we can do that. You guys have done a couple of those, you'll do some more, but when we use the trapezoidal rule and get an area back, we know that our area is at least that close to the actual perfect area. Okay? But better yet, probably a more useful and real world situation would be one where we start off with some kind of a tolerance. Say that we need to get the area to within 1,000th or something like that. How many trapezoids do we need to accomplish that? All right, so let's try one like that. What if we've got something like, let's say, oh, our area needs to be accurate to within our error needs to be less than or equal to, let's say, 0.0000. How many zeros do we want? Let's do that. Okay, lots of zeros. And what are we using for our? Doesn't really matter. We'll just go. How about? What if we do? Well, we already did this one. Let's just do that one. Square root of x plus 1
from, let's go from 1 to 4, how about? So how many trapezoids are we going to need to get this thing right? Okay. So we need our error formula. Now, what's f of x? Square root x plus 1. So what's f prime of x? Now think of that. What power is that?
X to the 1 half.
Okay. Okay, so what do I need out front? 1 half. Okay, 1 half times the quantity x plus 1 to the minus 1 half. And so f double prime? To the, okay. Okay. Good. All right, now our interval goes from 1 to 4, right? And so we need the absolute value, or we need the maximum of the absolute value of our function on that interval, right? Now we could probably power our way through this one without, and we will. We'll finesse our way through. Well, let's look at the graph first, and then kind of in hindsight say, now how could we have maybe not even needed to graph this thing? You tell me. But first, let's just try this with a calculator. So if I graph this, negative 0.25 times the quantity x plus 1 to the negative 3 halves. Okay, and when I set up my window, from where to where? 1 to 4. Why not? Let's just cut the window to the exact, right? So if we go window, positive 1 to positive 4, what's the next button I push? Grab zoom fit. Absolutely. Let's stretch this thing out over the whole screen. Zoom 0 for zoom fit. And that's what it does. Okay. Now let's just take a glance at the window and see where we are if we can orient it. Looks like we're negative, aren't we? Y min. Okay, so how about if we're going from like negative something very small, negative 0.08 to negative 0.02. So how about if we go to Y maximum? Let's make that positive 0.01 on the graph, so we can see the x-axis in there. Okay, so now where is the absolute value of the function going to be the biggest? In other words, where is it furthest from 0? It's at 1, right? At the lower, does everybody see that? When we're looking for this quantity, the maximum of the second derivative, of the absolute value of the second derivative of our function, think what an absolute value of a number means. The absolute value is just the distance from 0, right? Positive or negative. And so we can see that right here, our function has a bigger negative value than it does there, doesn't it? Right? So we know that that's where we want to evaluate the function, at 0. So we can do that. We can just go trace 0, or second calc value 0. Oh, not 0. It's at 1, isn't it? Sorry. Yeah, so I got to go 1. And it tells me the value is negative 0.08838883. You know, I'm a little uncomfortable with that, though, for one reason. Can you tell me what? There's something I don't like about that. We could probably use it, but why am I not super excited about taking that number and plugging it in for this?
Well, could you convert that into a fraction? Would that make it
Okay, and why is that better?
be less messy?
Less messy and more exact. Yeah. Well, the problem with this is that's a rounded number, isn't it? The calculator has already done some numerical stuff on that and given me back an approximate number. It's approximate because it's decimal, right? So really, I don't even probably want to use the calculator to evaluate what the value of the second derivative is. What I'd rather do is just find out the x value where it's going to be furthest from 0, which we said was 1, and then plug that in down here, right? Does that make sense?
Yeah.
That's kind of wordy, but I want to get an exact answer for that. Eventually, we're going to turn that into a decimal, but this is a great rule, and this applies almost more in science than it does in math. But people sometimes make this really complicated in science, but here's the rule. I'm just telling you, this is the rule on how you do calculations in science and minimize propagated error. The way to do it, absolutely the way to do it, is to only round once. If you use errorless numbers until your final calculation, then you can always just round to the appropriate number of sig figs once, and it makes it so much easier and so much better. That is the way to do it, I promise you. So f double prime of 1 is negative 1/4 times 2 to the negative 3/2. Okay, that's the magic number. That's perfect. That's the exact value that we want in our formula. So we'll put that in at the end. Now, what's our error going to look like then? So our error is less than or equal to b minus a. What were those? 4 minus 1. So what power? Good. B minus a cubed over 12 times n, which we don't know yet, do we? 12n squared times this, right? Times negative 1 over 4 times 2 to the 3/2, if I just put that down on the bottom.
Yeah.
Right? And we want that to be less than or equal to that ridiculously small tolerance I gave you, right? That has to be less than or equal to 0.00, how many zeros did I have? I forget. 6 zeros? Oh my goodness. Wow, that's going to be 10 million. Okay, so my goal here is just to solve for n. Right? Now, what do I do to get n by itself? Yeah, what do I do? If I want to get that n by itself, there's a couple ways algebraically to do this. There's some pretty simple ways. All I'm trying to do is, really, if I can just get that by itself and then square root my answer, right? How am I going to get the n squared by itself? It needs to be on the top by itself. You can, we could do something like that. We could cross multiply or exchange diagonally. Now, then that would work. That's a great idea. I'm going to recommend you just do it this way. I'm going to recommend that you just flip both sides to get the n squared on the top, and then algebraically get rid of everything attached to the n. But when you flip an inequality, you got to be careful. You have to flip the sign, don't you? Because now let's take a quick example. What if I have something like 1/4 is less than 1/3? When I flip this around, I get a 4 on this side and a 3 on that side. Notice that changes, right? So when we flip this guy around, we're going to get our 12n squared over, let's turn that into a number. 4 minus 1 is 3 cubed is what? Okay. And then over here we've got we could now change that. Oh, you know what we did? This is supposed to be an absolute value, right?
Yeah.
So that's positive. Right? Right, my mistake. So that should be positive. So we flip this, and we're going to get 4 times 2 to the 3/2 is greater than or equal to, don't even bother, just leave it as, make that a reciprocal. Just 1 over some really small number. Calculator will take care of turning that into a big number. Let it do the hard work. Okay, so all we have to do then in our final answer is what? Let's get that other stuff over there, right? So I'm going to multiply by 27/12. So on the other side, what am I going to get? Well, I've got a 27 on the top. On the bottom, I've got a 12 times that. 4 times 2 to the 3/2 times that, right? So n must be the square root of all that stuff. Well, that looks ugly, but it's just a number. Throw that in the calculator. Let's get an answer. Okay, so we got square root of 27 divided by, what do I absolutely have to have here? Quantity. Quantity. 12 times 4 times 2 to the 3/2, get out of the exponent, times,
You want to close your quantity there?
I gotta get that in there first.
Oh, really?
Yeah. Times 0.1234561. Close the bottom, get out of the square root, enter. Wow. Okay, that's a lot. Okay, now if n has to be greater than or equal to 1410.22 blah blah blah, what's the minimum number of trapezoids that we need? 1411. Make sense? 1410 can't guarantee it. That's not quite enough. It'll take a little more than 1410. But trapezoids come in discrete numbers, so we've got to bump up to the next one. Make sense? Yes. Oh, no bells. All right. No bell practice.